Ottazzi, who are Finnish mathematicians, and we have been working with them looking at Lie groups using methods from metric spaces. So what should I talk about? I am going to talk a little bit about groups that act on metric spaces. So I start out with a metric space, and then I look at groups of isometries on that, or I can start out with a group, and then I can try to put a metric structure on the group. So there are two ways in which I can think about this question. So a metric space, and I believe that in Kuwait you have a course for the students in the third year about metric spaces, and you define what is a metric space. So it's a space M for metric, and it has a distance function D, and the distance function just tells us the distance between points. It has to be positive. It's 0 only if the points are the same. The distance from point X to point Y is the same as the distance from point Y to point X, and so on. There's also the so-called triangle inequality for distances. So this is a very well-known notion, and maybe not quite so well-known is an isometry of a metric space. So this is a mapping of the metric space to itself that preserves the distances, in the sense that if I take 2 points X and Y, then f of X and f of Y are at the same distance as X and Y. So it doesn't move them any further apart or any closer. And the same is true if I take the inverse. And what else? I guess metric dilation. So a metric dilation is something that if I take a metric space, it makes it get bigger in some sense, or it makes points get further apart. So there's some number S, the dilation factor. And if I take 2 points, X and Y, and then I dilate them, delta X and delta Y, then they are S times as distant as the original points, X and Y. So these are quite reasonable and not too difficult, I hope, definitions. And so these are what I'm going to need about metric spaces. So let's have some examples. So if I just take the usual space of vectors Rn, then I can put different distances on it. I can have a distance that's d1, or a distance that's d2, or even a distance that's dp, where p is a parameter, and I add up the modulus of the distance between the different coordinates to the pth power, and then I divide them out. So this is a kind of a distance, and if I take either p equals 1 or p equals 2, then translations are always isometries of this space. They don't change the distances between points. And when p is equal to 2, this is the usual Euclidean distance, and rotations are also isometries. But if p is equal to 1, then only rotations through 90 degrees, 180 degrees, and so on. So here's a map of an American city. And you can see that if you want to go, I hope you can see my pointer moving around on the screen. If I want to go, say, from a point here to a point here, then I can't, unless I'm a bird, I cannot fly directly like this. I have to go along one of these streets and then up another one. And so the distance that I have to walk is the sum of the change in the x coordinate plus the change in the y coordinate. I don't have to go necessarily this way. I could also go something like this and like that and like that. But I would still end up walking the same distance or possibly more if I chose to take a long route. But this distance here, this map, if you rotate it a little bit, it doesn't look very similar. If you rotate it through 90 degrees, I could turn my computer through 90 degrees, but I don't think that you would be able to see that on your screen, so I won't do that. But you can really only, with this metric, with this distance, you can really only rotate through certain angles. So now let me go back to full screen. So that's an example of a metric space. And then there are lots of other standard examples, and maybe some examples that are not quite so standard. So the unit sphere in the space in Rn, in the space of all vectors, that's also a metric space, and that can have either the distance d2, the Euclidean distance between points, or I can have another distance that I'll call ds for spherical distance, which is a cosine, an inverse cosine of an dot product. So let me draw a picture of, I'll show you a picture of this one too. So here I have a unit sphere, and I have two vectors on it. And if I want to go between this point on the sphere and that point on the sphere, then the best thing to do is to go along a circular path. And the distance along that circular path, if this is a unit sphere, is actually the same as this angle in radians. And this angle in radians is the inverse cosine of the dot product of these vectors, which is where that formula came from. But if instead of a person or an aeroplane or a sailor or something like that, if I could actually, if I was a worm or something and could eat the earth, then I could go the straight distance going into the earth between these 2 points, and then that would just be the regular Euclidean distance. And that's another possible distance that I can put. So there are lots of examples of metric spaces, and those are just some of them. So I have to do F11. Keep going again. Okay, so here's another example to say that things are a little bit more complicated than that. So people who work in partial differential equations and work on so-called subelliptic differential operators, they often work with nilpotent Lie groups. So here's the Heisenberg group H is a nilpotent Lie group. As a topological space, it's just the complex numbers, Z for complex number, and T is a real number. So it's just a three-dimensional space, but it's got a rather funny multiplication. So if I multiply things, I just add, but then in one of the coordinates, I add a little factor that depends on the other coordinates. And that makes it into a non-commutative Lie group. And this group is by the people who work in subelliptic differential operators. It's given the so-called Corani distance, and the distance of a point zt from 0, 0, which is the origin, the identity of the group, is given by a fourth power or something and a square or something else, and then I take a factor 1/4. And so that's another example of a metric space, and it's actually an example of a Lie group that has a metric space. And then there are people who work in complex analysis, and sometimes when they are working on the unit ball in complex n-dimensional space, then they have another distance that is given by this formula here, which is not the same as either the Euclidean distance or the spherical distance, but this is yet another distance. So what I want to say is that the metric spaces are very simple things, they can actually encompass examples that are interesting to people in a whole lot of different areas. So my last example is another example. I'm generalizing really. I can take the group of all invertible real n by n matrices. I call that GLNR, group linear n by n real matrices. And as long as if I take real matrices that are invertible, I can multiply them and I can take inverses. And so I have a group of matrices. And we can make this into a metric space by defining the sum of the squares of the distances of the differences of all of the entries, and that makes it into a metric. And what is probably more interesting is that we can also define a metric that is left translation invariant. So if I take x points x, y, z in this group, the distance between x and y is the same as the distance between zx and zy. And a group with a left translation invariant metric with a metric that satisfies this property, we call it a metric group if it's also a subgroup of this group of matrices, and I'll call it a closed subgroup, I'll call it a metric Lie group. So it turns out that the vector space Rn and the Heisenberg group that I talked before are other examples of metric Lie groups. So lots of examples, lots and lots of examples. Okay, so if I have a metric space, I want to make a group out of this. And so here is a theorem which is by Van Danzig and Van der Waerden. It's from 1928. This is almost 100 years old. This is one of the very first theorems about groups and metric spaces. And it came about because in 1905, a famous mathematician by the name of Hilbert came up with a list of many problems. And one of his problems was about topological groups, and he wanted to know if every topological group that looked topologically like a Euclidean space could actually be made into a Lie group, so it could be turned into a subgroup of a group of matrices in some way. So there was quite a lot of research about topological groups in the early 1900s as people tried to solve this problem of Hilbert, and eventually it was solved through the work of many people in around about 1950. But this theorem from 1928 says if I take the collection of isometries of a metric space, if I take two isometries and take their composition, it turns out that's another isometry, and the inverse is also an isometry, more or less by definition. So it is in some sense going to be a group, but it's also what we call a topological group. It has a number of different topologies. So when we have a collection of mappings of a space to itself, we can put different topologies on it. One of them is the so-called pointwise convergence topology. One is called the compact open topology. And another one is the topology of uniform convergence on compactors. But all of these topologies end up being the same thing on this group of isometries. And so somehow that seems to be the right topology to use. And then with this topology, it's a topological group. That means that it's not only a group and a topological space, but there's also a nice interaction between the group structure and the topological structure. So it means that if I take the function of taking inverses of elements, that's a continuous function. And also taking products is a continuous function. So there's a nice interaction between the topology and the groups. And Van Danzig and Van der Waerden also discovered that we could put a metric on this that is another example of a left invariant metric. So if I take three isometries, F and G and H, then the distance between G and H is the same as the distance between FG and F of H. So this is another example of a left invariant metric on a topological. So this is a very old theorem, and for quite a long time, nobody really paid very much attention to it. But apparently, well, in the last 30 years or something, then people have been much more interested in it. So it just goes to show that you can write a mathematical paper that it seems that nobody's really interested in, and then many years later somebody discovers and says, that's quite interesting, quite important. So if we have a metric space, we say that it's a homogeneous metric space if the isometry group acts transitively on it. That is, if I take 2 points in the metric space, then I can find an isometry that maps one point to the other point. So from some sense, that means that all points look to be rather the same. So this is homogeneous. So the examples given before and the isometry group itself are examples actually of homogeneous metric spaces. In real life, nothing is really homogeneous. Nothing is quite as simple as that. If we go back a little bit to the map of the city, this kind of space is quite interesting. People who are scheduling deliveries will actually spend quite a lot of, if you have a truck driver who's going to be driving to lots of different places and delivering things, and he has to deliver something here and something here and something here and something here, then you want to find the route that he can take that is the shortest route, because that's going to mean that he consumes less, probably can do it quicker, and so there are a lot of advantages in this. And so, in fact, in the real world, there are people who study optimization, and the optimization problems here can be in cities like this. But as you can see, actually, in this city here, you can also take some roads that are not quite always in this north-south or east-west direction. And I looked at a map of Kuwait City, and I see that Kuwait City looks more like a normal city to me. That in the American cities, all the roads go north, south, east, west. But in normal cities, this is not the case. And so anyway, that's the real world is like this. So in the real world, people might use the sort of abstract metric space as a model, but then again, they might find that the model is not really quite accurate enough. Okay, so metric spaces, isometry groups, real life is not homogeneous. So here's another example. So I can take a finitely generated group. Finite groups are examples of these, but also the integers are examples of these, or discrete lattices, such as a finite product of copies of the integers. So I can look at the set of n vectors, and they all have got integer entries, and I can add these up, and then this is another example of a group, a finite group, a finitely generated group, because any vector that has got integer entries, I can start out with these vectors here, and I can add finitely many copies of this one, and maybe subtract finitely many copies of that one, and in the end, add a few copies of this one, and I can, by doing that, I can get to any other any vector with integer entries that I want. So this is an example of a finitely generated group. And in the language of group theory, every element of the group can be written as a product of one of the generators to some power, another generator to another power, another generator to another power, and so on, where these S1s and S2 are in my generating set. And the entries here I just take as being plus or minus 1. So I can take either a power 1 or I can take the inverse of that. So if I had these basis vectors here, instead of taking 1, 0, 0, I'd be allowed to take minus 1, 0, 0, 0. And then I end up adding these vectors. That's the thing that corresponds to multiplying in a multiplicative group. So then I define that the length of an element G, and this is a length that depends a little bit on the generating set, so I've called it the S length. I write that to be the smallest K so that I can write it in this way with S1, S2. So somehow the idea is that each of these things where I've got a plus or minus 1 corresponds to moving in one direction or another direction at distance 1. And then when I've done all of these things, I've moved to total distance K. And so this is a definition of a length in a group, and this is something that is of some interest in group theory. In fact, there's an area known as combinatorial group theory or geometric group theory in which one looks at groups in this way. So if I take the collection of all of the elements of G of length at most K, then I can think of that as being like a ball with a center at the identity of the group and of radius K. And we say that if I count how many elements there are, there shouldn't be an S there, I'm sorry about that. If I count how many elements there are in this ball, then it can grow in different ways. If it grows like some power of K, then we say G is a polynomial growth. And although apparently polynomial growth might depend on the set of generators that I take, it turns out that that is not the case. So that is a way to look at length in groups, metrics in groups, lengths in groups, and to define the idea of polynomial growth. So this example here is of polynomial growth. But it turns out that if I go back to my example of n by n matrices, if I go back to my example of n by n matrices and try to make this, then if I consider the matrices that I can take a generating set for this that has just got entries of 0 and 1, and then it turns out that this is an example that is actually not of polynomial growth. So when there are examples of polynomial growth and there are examples that are not of polynomial. So Gromov's polynomial growth theorem is about groups that are of polynomial growth. So just before I say what it is, I need to just remind you what is a nilpotent group. So if I've got a group with an identity, and if I take a subgroup of that, of a subgroup H of G, then I can take the commutator subgroup between G and H, and that's defined to be the smallest subgroup of G that takes all the commutators X, Y, X minus Y, y minus 1, where x is from G and y, that should be y, is in H. So I take commutators with some things in G, some things in H, and then I get a whole collection of commutators, and then I take this smaller subgroup that takes all of those commutators, and that's the commutator subgroup GH. So if I have a group G, I can define the lower central series, so which is a collection of subgroups, G1, G2, and so on. G1 is just the group itself. G2 is G commutated with G. So it's really all the elements that can be written as commutators. And then I can take G3, which is the commutator of G and G2, and that's all the things that can be written as commutators of three things in some sense, and so on. And inductively, Gj plus 1 is the commutator subgroup between G and Gj. So a group is nilpotent of class J if Gj plus 1 is equal to E. Basically, that means that if you write down some very long commutators, so a commutator, writing down commutators, even if I take two elements, it gets to have four things in it. And if I start writing down more elements, it rapidly gets quite a lot bigger. But if the group is nilpotent, then all the really long commutators have to be trivial for some remarkable property of the group, nilpotence of the group. So Gromov's polynomial growth theorem says the following, that if I have a finitely generated group of polynomial growth, then there is a subgroup G0 of the group G, which is a finite index, the quotient space G over G0 is finite, and G0 is nilpotent. So the group is almost nilpotent. So this says that groups that are of polynomial growth are almost just nilpotent groups. And this was considered to be a very important theorem when it came out. It appeared in 1981, but it was announced before then, and for quite a few years, for at least 20 or 30 years before then, people had been trying to prove this, and different people had proved different things about it. And when Gromov finally proved it, it was one of the things that made many people feel that he should have had a Fields Medal or something, because it was a very remarkable piece of work. So since it is a very remarkable piece of work, it seems reasonable of me to pay a little bit of homage to Gromov and to tell you a little bit about how the proof of this theorem works. So I define the distance between 2 points of the group to be the length of G to the minus 1h. And when I do that, then the group with this distance is an example of a metric group. So that is to say, a group that's also a metric space, and the metric has some nice invariance properties. And what Gromov did was he invented a way to rescale GD to obtain a new metric group that now gets called the asymptotic cone. And it's a connected topological group with a dilation. It's very much like the Heisenberg group that I gave you as an example very early on. So what do I mean by rescaling? Well, I have to ask you now to use your imaginations and to perhaps to take a little piece of paper, and on this little piece of paper to draw a number of dots, one next to the other, all in a straight line. Now, if you then imagine that this piece of paper is infinitely long, then you have, in some sense, a copy of the integers with all of these dots. Now, if you look at that piece of paper from very far away, then the dots seem to be closer together. So looking at something from far away, is a way to somehow make it seem that things are getting closer together. And that's what I mean by rescaling the group, changing the point of view so that it looks that the points are getting closer together. Now, if you take all the dots on this line and you keep on making the dots get closer and closer together, then in the end, you end up getting something that looks like a whole straight line. And Gromov's process is to take a much more complicated system of dots and to rescale them and to get a rather more complicated limit, which turns out to be a topological group with a dilation. So that's a process that is reasonably easy to describe, but it's quite technical to do it correctly. And well, there are even doubts that maybe Gromov didn't quite do it correctly, but the ideas were all very good and very correct. It's just that Gromov tended to write things that were not very complete in their arguments. If we had students who wrote exams like this, we would be a bit upset. But anyway, so after he worked out this way to rescale, he showed that the limiting group that you get that has dilations is nilpotent. And so somehow some kind of limit of the group is nilpotent, and he can use that to say that the original group was also nilpotent, was almost nilpotent. And I can try to explain why almost nilpotent means that it's got a subgroup of finite index. If you take your piece of paper on which you have drawn this infinite line of dots, on your infinite piece of paper, all at equally separated, and then you draw another parallel set of dots, parallel to the first ones, then this is somehow more like an original group. But if you go through this process of shrinking everything down, then two parallel sets of dots, when you make them get closer and closer, just turn into one set of dots. So that's somehow what happens in this process. So that's Gromov's proof, Gromov's famous polynomial growth theorem. So here's something that is a little bit technical, but let me tell you anyway. So we say that when we've got metric spaces, we often use an idea called quasi-isometry. Quasi-isometry, something that's close to isometry, but it's not exactly isometry. And so two spaces are quasi-isometric with constants L and C if I can write down an inequality like this, that the distance in the new metric space between the images of 2 points is related to their distance in the original space with some constant L here, L to the minus 1 there. So actually L to the minus 1 is going to be small and this is going to be big. And then there's some other additive constant as well. Anyway, this is a technical definition. It doesn't really matter exactly what it means, but there is a notion of quasi-isometry. And then if one looks very carefully at Gromov's arguments, then if you take a group G and you take different generating sets, and the different generating sets give you different ideas of length, and the different ideas of length give you different metrics, but the group with one metric is quasi-isometric in this technical sense to the other group. And it means then that the asymptotic cones of these two things are quasi-isometric, and that actually implies that the asymptotic cones are isomorphic as groups. And there was a student of Gromov called Pierre Ponceau in France who did a lot of study of quasi-isometries of these asymptotic cones, and a lot of the very important developments that came out of this theorem of Gromov are due to Ponceau. So anyway, I wanted to say that in the work that I want to talk about now, which is with Kivioja, Donne, and so on, we deal with something that's called 1C quasi-isometry. So I can put a constant one here and a constant one there. So then I deal with a 1C quasi-isometry. So it says that it changes distances, but it only changes them by a finite constant. So here are some questions that come out of Gromov's work. So first question, what can we say about the structure of a connected metric space that has a dilation? So in Gromov's work, there was this structure, the asymptotic cone, which was a connected metric space with a dilation. It was also a topological group. So by Gromov's work, if you get a connected metric space that's got a dilation, then it has to be a nilpotent group. But what if it's not a group? What if we just take a connected metric space that has a dilation? What can we say about that? So that's a question that arises out of this work of Gromov. And another question is that if I take two connected metric groups, so I take two groups with metrics, and I just say that they are isometric or quasi-isometric, which is a weaker form of isometry, and say these two groups are similar in a metric sense, in a distance sense. Does that mean that the two groups are similar in an algebraic sense? And this question gets asked because of Gromov's work. If we get two groups that are asymptotic cones, and therefore they have dilations, and if these are quasi-isometric, then they're actually isomorphic. But what if we take two groups that are not asymptotic cones? So the work that I want to talk about a little just in the last part of my talk is, go away, is something. So here's something that is probably quite well known. If I take any n by n matrix, then I can factorize it as a product R times Q. R is an upper triangular matrix, and Q is an orthogonal matrix. So this is something that you learn in a course on matrix algebra, and it's actually something that's considered to be quite important. So I went to Wikipedia and looked for the decomposition and how you can do this, and you can look at this factorization of groups or this decomposition of things, and you can use the Gram-Schmidt process to do it. You can use Householder reflections. You can use Given's rotations. It's something that's actually of interest in areas such as engineering, and so because of that, actually, it's good to know something about it, and that's, I guess, why we say something about it when we do courses in linear algebra. So every matrix, every invertible matrix is a product of a orthogonal matrix and an upper triangular matrix. So if I let UT and R be the group of all upper triangular matrices and O and R be the group of all orthogonal matrices, then in some sense we've written one group as some kind of product of the upper triangular matrices and the orthogonal matrices. One of these is a solvable group and the other one is a compact group. That's just the way it is. If you take orthogonal matrices, then the entries are always bounded, and that tends to make things compact, and the other one is solvable. So that's just a way of looking at a process that something that we do in linear algebra. And so here is a lemma. This is just a technical lemma. If I have a metric Lie group with a compact subgroup, if it's a metric Lie group, then that's to say it's a metric group. This means that this metric D, has a left invariance property. D of GH prime is the same as D of H prime. But if I've got a compact subgroup, then I can take this metric here and modify it a little bit so that the new metric has got a double invariance property. Not only is it invariant under left multiplications by G, but it's also invariant under right multiplications by elements of this compact subgroup. So I can take a metric Lie group, I can find a new metric on it that has this extra property, and the one group and the other group, well, it's actually the same group with one metric and the new metric, then these are quasi-isometric, which means that they're almost the same. So that's a little technical lemma. And then I guess I even said something about the proof. Okay, so the major difficulty is to define this new metric. And the new metric is defined in terms of infs and sups and so on. It's not something that you just sort of, it's not something that you can see immediately. Once you see this definition, then it turns out to be possible to work with it and to prove that this is true and that the new metric is not so far from the old metric. But you have to have the right definition first. Okay, so here is the first theorem of myself, Kivioja, Donne, Nicolussi, Golo, and Ottazzi. So if I take a metric Lie group with a factorization S times K, so S is one closed subgroup and K is another one, and this has to be a compact subgroup, and this metric has to be like the metric that I constructed in the lemma. It has to have two invariance properties, a left invariant property and a right invariance property. But if the metric satisfies this property, then I can take the direct product of these two groups. And if I take the direct product, it's not quite the same thing as the original group G. In the direct product, everything here commutes with everything here. But in the original group, the orthogonal matrices and the upper triangular matrices usually do not commute. So this is actually a different group, and this different group has a metric that is isometric to the group that I started out with. I start out with a group with a factorization like this, and then I can produce a new group in which these factors actually commute, and these things are isometric. So the point about this is that I can get two groups that are quite different in terms of groups, in the sense that in one of these factors commute, and in the other one they don't commute. But they're isometric, they have the same distance structure. And once again, for the proof, you have to know how to define the new metric on the product group, and there's the formula for the new metric. And once you have this formula, then in fact it's possible to prove that it has the properties that I claimed. So let me comment about this. Actually, there are some examples of this one due to John Milner from the 1970s, and then to Agrachev and Barilari from about roughly 2005 or something. But these guys produce rather more complicated arguments and difficult metrics. So the fact that we can have groups that are isometric that are not isomorphic suggests that Gromov's idea of technique of using metric space ideas to prove group theoretic results is not necessarily going to be applicable in other settings. Because in his setting, it was quite important that isometric groups, even quasi-isometric groups, were isomorphic, but that's not the case for us. And so here's the last theorem. And now if I take a locally homogeneous metric space. So I take a metric space that is homogeneous. So it looks the same from all points. And if it's got a metric dilation, then it turns out that actually there is a nilpotent metrically group and a dilation on the nilpotent group, which is also a group isomorphism and a metric dilation. And these are essentially the same things. So this is saying that this is a little bit more general than Gromov. It's saying that if I get some, Gromov started out with some metric groups, and I'm saying that we can replace metric groups by homogeneous metric spaces, and as long as they've got dilations, then essentially they're nilpotent groups. So here is a proof of this. It's more complicated. It uses Lie groups and Lie algebras. I don't know whether you want me to spend a lot of time on this. I think maybe I will just spend about 10 seconds on each slide just to show you that it can be done. So first of all, we have to do something about there is a fixed point and there is a Banach fixed point theorem. And that is something about metric spaces. And then the metric space is proper and doubling. One of these means that balls are relatively compact, have compact closures, they're not too big. And the other means that a ball of radius twice r can be covered by finitely many balls of radius r. And to see both of these things, we do them by checking that they're true when r is very small, and then we can use the dilation to prove them when r is very big. So here's almost the rest of the proof. Then we have to show that M is a contractible manifold and G is a Lie group. And I'm not sure if I really want to go through this, and I'm not sure if you really want me to go through this. So maybe actually I will just leave it here, and then we have time for questions and discussion and so on. So let me stop now. Thank you.
Thank you, Professor Cowling, for this inspiring talk. I'm sorry that you cannot hear the clappings. I'm sure that everyone is clapping for this. This is one of the disadvantages. Maybe there is someone from the audience who would like to ask something about these proofs or anything else.
Can I ask about?
Absolutely.
First of all, thank you very much. It was very clear. I was, well, I'm a kindergarten teacher, let's put it that way, coming from physics. I was looking, I have read Gromov's papers and the hyperbolic groups and everything. Can you first make some comments regarding, your view is Lie theoretic. Do you have any geometric intuition about your theorem? It appears that you play with nilpotent. Somehow your proof reminds me of Gromov's proof, this Zassenhaus Riemann, which things are almost nilpotent in a small area. But could you please, if it is possible, elaborate on the geometric meaning, if there is any, or a geometric picture?
I'm afraid that I'm not as clever as Gromov. I think you have to ask Gromov this question, and then he can.
Yeah, good luck finding. Okay.
The trouble with asking Gromov things is that the answers are usually so complicated that that they're not very easy to understand.
I know.
But, I mean, I guess that I don't know. Let me say one thing, and that is that Gromov says that if you take any theorem about groups that is true for all groups, then it must be trivial. So he likes to think that unless there's something very special and very particular about what's happening, then it's somehow it's too general and too easy. And so I guess that in this thing about the nilpotent groups, well, what is special about nilpotent groups? Well, in terms of this so-called polynomial growth, they're very special. So that's certainly one thing. It means from a sort of an algebraic point of view that the groups are not too non-commutative. Right. But what it means from a geometric point of view,
they are almost flat. The sectional curvature, they are almost flat, right? Gromov's almost flat manifolds paper, 1977. Journal of Differential
Yeah. They're almost flat. So they're all. It's almost like Euclidean space.
Right.
So I guess the intuition is just that. It's just that nilpotent groups are not so far from being Euclidean.
Okay. Could you please be kind enough to provide the reference of your paper, the CKLNO paper?
Sure. So it appeared on the archive.
Archive, yes. If you could give the archive number, it would be great.
This morning.
Today?
So let me check. I can find
I will find it. If you tell me it's in the archive, I will find it.
Okay, but it went on the archive this morning. So
okay, I will get it.
It's there now. Yes.
Okay. Thank you very much.
Okay, no problem.
Thank you, sir.
Any other questions to Professor Cowling for his talk or general questions?
Well, sorry to bother you again, but somehow whatever you say, when you speak about dilations, yes, I'm prejudiced. I think about this Abrimanian Carnot-Carathéodory geometry, this kind of
right, thing. Yes.
So this must somehow be related, right? Somewhere it should be lurking over there, especially Agrachev and Barilari scream about Subrimanian. And also your work in subelliptic operators.
In fact, their examples are proved using sub-Riemannian geometry. But from my point of view, I mean, sub-Riemannian geometry is very nice and it's very powerful,
right.
But it's actually more complicated than some other sorts of geometry. There are some things that I said at the beginning of my talk. I took the Heisenberg group with this so-called Korany metric, and so on this page here, this group with the Korany distance, or the research in complex analysis uses this complex distance. Neither of these are sub-Riemannian distances. They're both on manifolds, but they're not sub-Riemannian. And one of the reasons is that there is a sub-Riemannian distance that's almost the same as this, but it's much harder to write down. As soon as you start to write down explicit formulae, you have sort of inverse cosines of cosines, and it's much more complicated than this and harder to work with. And similarly, there's a sub-Riemannian distance here. So the sub-Riemannian world is is a nice world, but it's very technical.
Right.
And if you can make things a little simpler by having simpler formulas to work with, then that's also a nice thing.
I'm sorry to.
You know, this is, I mean, if you come from physics, you know, you're looking for models, and you know, the simplest model and the model with the simplest formula is the one that in physics you say is the right model because it's the most beautiful and the most simplest and the easiest to make predictions with, and so on.
Right. Yes. Thank you very much, sir. Thank you.
Okay.
Any other questions to Professor Cowling? If I can ask Professor Cowling a very general question, as I can see from this subject, the gap conjecture is still open, which separates the nilpotent groups from other groups. I mean, potentially. I mean,
yes.
Apart from this, are there any problems, research problems, which are not so difficult, like the gap conjecture, and they might be attractive for a young researcher? Is this topic? I mean. Does it offer many problems?
I have my colleague Enrico Donne, who is now a professor in Switzerland, has had a number of PhD students who have all been working on problems with metric Lie groups, metric geometry, and so on. And since they've all managed to get PhDs, at least so far, then it suggests that there are at least a number of reasonably accessible problems for them to look at. So I mean, you know, not all problems are as difficult as the gap problem. One of the problems in mathematics, of course, is that, you know, there are some very difficult problems, such as Fermat's last theorem. And of course, if you prove this, you become very famous. But there have been very many people who have spent a lot of time trying to prove it without managing to prove it. So, you know, you have to pick on something realistic to do when you are, particularly if you're a student and trying to do a PhD or something like that. But no, there are in this area, I believe there are quite a lot of problems, and Enrico is very good at finding problems for his students, for instance.
It's very nice to know that this is not an elite subject only for a few people in the world. I mean, we will definitely try to search for such problems. I mean, from your references. Thank you very much. Yes,
can I also ask something else? You mentioned about asymptotic cones, right? From asymptotic, then yes. any compact group is a point.
Yes.
From that viewpoint, therefore, your concern or your target are non-compact groups, I assume.
Essentially, yes. If you work the sort of the 1C quasi-isometry that we work with, right, sort of says that you see the large scale structure of things quite accurately,
right,
but the small scale structure of things you don't see anything at all.
Right.
You know, but this from the point of view of physics, you know, the way that we see the world, we don't really see the, you know, the sort of the quantum effects that are happening. Right. We just see the large scale structure.
Okay. And last but not least, I know I am abusing this because I have monopolized all the questions.
No, it's great questions. They're very nice. Thank you very much.
I don't think I have the right to do that. There are many
have
people
the right,
over there. What would be the last question? I have not read your paper, therefore I cannot even conceive the metrics. But for me, metric means something. I have a synthetic viewpoint, sort of like the Russians, right? Many people. So the soups and the infs are excellent, but could you draw something in a synthetic sense, right? To give some intuition about the metrics that you have defined, this decay and stuff like that. Is it reasonable? First, of course, I know I have to read the paper and see basically what it says, but is there any intuition behind the definition of these metrics? Any visual in quotations intuition?
In some of the things that we do, yeah, there are definitely. So in some, say in this one is definitely quite, that one's really quite geometric. This one here, yeah, when you write it down with instance soups, it's not very clear, but you can think of, you can take points G and G prime, and then here there is both these things have right K orbits. So you multiply just by elements of K on the right.
Right.
And then you're talking something about the distance between 2 points on the K orbits. And so you're sort of saying if you move one of the points to somewhere, and then you take point on one of the orbits, and then you take the furthest point on the other one, and then you go back to your first point and you try to make it so that the distance of the furthest point from it is, I mean, you can look at it in terms of points on orbits and trying to get furthest.
Okay. All right, I will.
Points.
Okay, thank you very much, sir. I will. I have to look at the paper. I will. Thank you.
Okay.
Thank you very much, Professor Cowling, for everything, for your time. I know that it's very late now in Australia. That's why I don't want to keep you more. We don't want to keep you more. I mean, and we really hope after Corona that you can visit us in Kuwait and give us some talks here as well. Thank you very much.
Well, I would be very happy to do that. I just hope that Corona doesn't go on too long.
Exactly. Warm greetings. I'm sorry.
No.
We would like to, on behalf of my department, I would like to thank you for this great honor and hope to see you soon.
Okay. So thank you very much for your very flattering comments, and I hope to see you soon too. Somewhere, who knows where, but you know,
Exactly.
maybe in the UK, maybe who knows. Anyway, so thank you very much, and I say good night, but for you it's good day, and yes. Okay.
See you.
Okay. So bye.
See you.
Thank you, sir.
Thank you very much.
Okay. Bye.